All right, so good morning. Welcome to Hydrogeology Geo 420. And today we're going to be talking about aquifer characterization. And I will put down the screen. That'll make it a lot easier for people to see what's going on here. Okay, so one of our chief jobs as hydrogeologists is to figure out how to calculate the flow of groundwater, right? And we need the head gradient and we need hydraulic properties, right? And in principle, the most important ones are going to be the hydraulic conductivity and the storage coefficients for our aquifers. So the way we measure these properties, you've been out and you've performed some of these tests, but the basic idea is to perturb the aquifer somehow and then measure the response. All right, so we put slugs in, we pump, we can do all kinds of different stuff. We try and get the aquifer to respond, and then we can use that data to calculate aquifer parameters. So, you know, in a nutshell, this boils down to some basic, or one of my fundamental science rules. And that is, if you want to be able to, if your job as a hydrogeologist, for example, is to try and predict how an aquifer might respond to pumping, then the best thing you can do as a scientist is go out and pump the aquifer and measure the response, right? So measure what you want to predict. That's the basic principle. Measure what you want to predict. And as much as you can do that, that's our job. So that's what we do. So aquifer characterization is essentially figuring out ways to measure what you want to predict and to estimate the hydraulic properties of the aquifer. So a lot of these revolve around pump tests. All right. And the basic idea is if we want to go out and just pump the aquifer and we want to see and measure the response. So let's consider here, we're going to start off with a confined aquifer. So here's land surface. I've got some confining unit here. And then I've got an aquifer. Down here. And I'm going to say that I've drilled a well. Down into the aquifer. And I've got this well screened over the entire thickness of the aquifer. So this is thickness B of my aquifer, and the well screen covers the whole thickness. And then I'm going to have another well or a piezometer at some distance over here. All right, and this piezometer just has a short screen here. And the distance between these two, we'll just call R. Okay, so before we begin pumping, we've drilled this well, and this is a confined aquifer, so the water level inside this well would rise up above the confining unit. We'll just put it arbitrarily here. And we're going to say that the head gradient before we start pumping is flat. All right, we're going to make the assumption that the head gradient is flat. And so we can envision that there's this potentiometric surface, flat potentiometric surface in our aquifer. At time 0. All right, and this is the water level. If we put a well into any place in this aquifer, it would rise up to this initial groundwater level. And let's call this initial level, we'll call it H naught. And here I'm setting Z equals to 0 as the bottom of my aquifer. So this distance here is H naught, and over my entire aquifer at time equals to 0, the head is equal to H naught. All right. Okay, so we come along and we want to pump this. So this is, M dot 2, here's M dot 3. We come here and we start pumping. All right. So when we pump this water, we're pulling water out of the well, right? So we have some discharge out of the well, Q. All right, so I'm pumping water out of this well. Where is the water coming from? Don't overthink it. The aquifer. All right. All right. I'm pumping water out of the well. It's coming out of the aquifer. All right. That means that I must have groundwater flowing into my well. Right. So I have to have groundwater flowing into the well. So in order for groundwater to flow from here into the well, what do I know about the head difference between the outside of the aquifer and inside the well? The head has to be less inside the well. All right. So as soon as I turn a pump on, I have to drop the water level inside my well, or else you'll never get groundwater to flow inside it. Right. So I start pumping, my water level drops inside the well. All right. And groundwater starts flowing from the aquifer into the well. What we see is after sometime t equals to T1, this lowered water table should be symmetric on both sides. That's terrible, but as good as it's going to get today. The lowered water table inside the well will extend some distance away from the well. And this zone here, where we've dropped the water table, is called the cone of depression. So this is the head or the potentiometric surface at some time after pumping T1. And our head here, so as pumping goes on, oftentimes the water level inside the well will remain constant most of the time, but this cone of depression will continue to expand. So this is time T2. And so our cone of depression is now bigger, which means now we're pulling water, you know, at T1, we're pulling it from this distance. And at T2, we're now pulling it from this distance into the aquifer. All right, so we have this, we drop the water level in the well. All right, it makes this cone of depression, and that cone of depression basically expands over time. And as we do that, we're drawing water from farther and farther away from the well. It's just the distance at which we're affecting or pulling water out of the aquifer. It's not necessarily intensity, it's just the fact that the longer we pump, the farther out from the aquifer we are pulling water, or from the well, we are pulling water into our well. So let's look at our head. Let's say this is the head inside our well now, our observation well. All right, and this is at, let's say, H2. So this is the head. The head started off at H0 inside our observation well, and then as pumping went on, it slowly dropped down, and at this time, T2, it's at H2. It's dropped below the initial water level. So now let's do some definitions. Let's define little s. I'm going to put an underscore here so that we know it's little s, which is we call drawdown. All right. And drawdown is just a relative change in the head. So we're going to define drawdown. It's defined as H0 minus the head at some time later, all right, after pumping. Okay, so what is my drawdown at the beginning of time before I start pumping? What is the drawdown in my observation well? Yeah, so at T0, my head inside my well is equal to H0, and so my drawdown, so S would be H0 minus H0, that would equal 0. All right. So if I haven't pulled my water level down, my drawdown's 0. Okay, at T1, my drawdown is H1 minus H naught. And I drew this cone of depression so that it really is ending right at my well. So at T1 here, what would my drawdown be? Say that the cone of depression ends right before this observation well. So, okay, so once again, it would be 0. And at T2, drawdown would be H1 minus H2. Now my cone of depression has expanded past my observation well. H2 is less than H naught. So my drawdown is greater than 0. Okay, so an important thing with drawdown, it's bounded. Well, I guess it's not really bounded. In a pump test where we're lowering the aquifer table, it usually starts at 0, always starts at 0, and it becomes positive as we lower the water table. You can actually, well, we won't get there. So we'll just say drawdown starts at 0 and usually goes positive. Okay.
Equation for drawdown as H naught minus H, like with T in the parentheses, but then later on when you like are writing that, you don't format it like that is.
Well, so at time 1, this would be H naught minus H1, which is the head at time T1. It's, if you want, I could format it. So Finch is saying, you guys can't hear them. I hear them. I forget that. So Finch says, hey, up here you said H naught minus H sub T. And here I changed to this other notation, H sub 1. So maybe I should, to be more clear, write this way, H at T1. All right, which looking up here, we said is equal to H naught. And instead of H sub 2, this ought to be H sub T2.
With that one, I was more confused as to why you did H sub 1 minus H sub 2.
Yeah, it should be always H sub naught.
Okay.
Always H sub naught. That's just typo. So Finch said, well, why did you start with H sub 1? Because I made a mistake. Okay. Let's define one other thing, and that is this distance over which pumping is affecting the aquifer. So past this distance here, if we go out past this distance, the head in the aquifer is not affected by pumping. So we call this distance where pumping is affecting the aquifer, we'll call it R sub I. This is the radius of influence. And in general, the radius of influence expands over time. All right. After really long times, it'll usually reach a steady state, but in general, the radius of influence expands over time as we draw the water level down farther and farther away from our well. Okay, so this is in cross-section view, right? And I just want to, I want to look down in map view really quick and look at the flow paths. And I'm going to draw a simple flow net around our well. All right, so this is cross-section view. Now let's look at map view. And we're going to say we'll do this at time t2. All right, so in the center of our map view, here's the well. Here's our observation well over here. And I'm going to draw head contours here. I'll draw them in red like we usually do. And at time t equals to 2, the H naught contour would look like a circle surrounding our well. All right, so this is H naught. And the distance of this circle is the radius of influence. So this would be the this is the contour at which my water level is equal to the initial water level. All right, and then we would have contours and these should be perfect circles. All right, and these are head contours, and the head is getting lower as we go towards the well. So now I can draw flow paths of water that come to the well. And they should be roughly perpendicular to our contour lines. Like this. So the key here is that we have radial flow to the well. All right. Water is coming from all sides radially into the well. Here's the contours of our drawdown cone, and the water is just flowing down that drawdown cone into our well. All right, so here is the basic idea of pump tests characterization. Once we define the boundary value problem that solves the groundwater flow equation for a given pump regime, all right? And then we use the solution. We match that solution to the data by varying the aquifer parameters. And once we find the aquifer parameters that fit the data the best, we say those are the aquifer parameters that best describe our aquifer. So let's do the simplest one. Well, before we go there, let me just write down the basic idea. find solution to the boundary value problem that best describes our experiment. So this is step one. And then step two, match solution to field data by varying K and S to get our parameter estimates. All right, in the parlance of geophysics, this matching our data gets called inversion. In groundwater modeling, it gets called calibration. In some math circles, it gets called parameter estimation. In engineering, it gets called optimization. All of these are the same idea. It's basically making your model or your solution fit your data. And you'll hear all these different words thrown out for it. All right, so let's start off with the equation for radial groundwater flow. Right, so the first ingredient we have to solve the boundary value problem is a governing equation. Can't solve this problem if we don't know what the governing equation is. So let's make some assumptions first. Homogeneous. Isotropic. Uniform thickness. Fully screened crossed aquifer. So if I have these assumptions, then my radial flow, if I I can try and draw this in 3 dimensions here. All right, here's my well. All right, here's my well screen. It's across the entire thickness of the aquifer. And I will have flow uniformly moving around my well. And if I'm homogeneous and isotropic, this radial flow will be the same all around my well. All right, and up and down the total length. So in that case, this reduces to a one-dimensional radial flow equation. And the governing equation looks like this: for one-dimensional radial flow for a homogeneous, isotropic, and uniform thickness aquifer. All right, this extra 1 over r dhdr, that's just what happens when you go from Cartesian coordinates to radial coordinates. All right. So this is essentially the same equation that you've looked at before, like d squared h dx squared. It's just that when you go from Cartesian coordinates to radial coordinates, instead of d squared h dx squared plus d squared h dy squared, you end up with this: d squared h dr squared plus 1 over r dh dr. It's just a radial coordinate transform. So here S is our storativity. And T is our transmissivity. Which, remember, is defined as K times B, where B is the aquifer thickness. All right, so for most of our pump test equations, this is the, or pump test, this is the governing equation that we will be solving. All right. You're not actually going to solve them. We'll be using solutions, boundary value problem solutions to this equation, but this is the governing equation we're solving. And in that case, all of these things apply. We've made the assumption that our aquifer is homogeneous, isotropic, uniform thickness, and fully screened across the aquifer. If those things aren't the case, then we will have a hard time fitting our data. All right, and we'll see how we deal with that in the real world. Okay. Let's start off with the simplest thing we can do, and we're going to say that we have steady state flow to a well. So this would be the case that we've been pumping an aquifer for a really long time, all right? And all the water that we're pumping out comes from recharge to this aquifer in external places. So the drawdown cone does not change. So we've been pumping for a long time. the discharge from our pump, Q sub P, is balanced by recharge R. So there's no change in drawdown. With time anymore. We have a static drawdown cone. Or cone, the cone of depression, it also gets called. Okay. So let me just draw a quick little illustration here. So we've got a confining unit, we've got this aquifer, all right, of constant thickness. We've got a pumping well that is screened over the full thickness of our aquifer. And I'm going to say I've got 2 observation wells. One at radius 1 and one at radius 2 away from this. And what we have here, after a long time, we've said, hey, my cone of depression is constant. And it extends away from my well. So I have this constant cone of depression here. All right, so if I have no change in head, what kind of system do we call this? We have a constant cone. Is this a transient or a steady state? Right, so we're in steady state here. All right, let's start off with the big Q form of Darcy's law. What is it? And here, I'm going to say dr, just because that's the radial direction away from the L. Q is equal to negative Ka dH dr. All right. Now, what is the area across which this flow is occurring? Remember, flow is coming all directions. Around this well. So what is the area across which the flow is occurring? Close. It has to do with the circumference of the well, but the circumference refers to a single, remember the circumference is basically like a line right here. So definitely has the circumference of the well in it. but we need to add another dimension. It's the surface area. It's the full surface area of this well that we're after. Okay, so what's the equation for the circumference of the well? And let me tell you that it has a radius of r sub w. And then how do I make this the full surface area of the well? Anybody know the equation here? Yep. We're just going to multiply it by the thickness of the aquifer. Boom. So that's the area. This right here is the area across which flow is occurring. Times dH dr. All right. I'm going to move quickly through this here, but I'm going to do it just because I think it's always good to show you why you should pay attention in calculus. Oftentimes we take calculus and say, oh man, we're never going to use that. Well, that's not true if you want to be a hydrogeologist. All right. All right, I'm just going to do a little bit of algebra here, and I'm going to get all my DHs on one side and everything that has to do with R. Q. On the other side. So I just did some rearranging here. Brought R and dr and K times B. What's K times B? Transmissivity. So I'm going to put transmissivity here. All right, so now I'm going to integrate. So I'm going to integrate from H1 to H2 dH plus Q over 2 pi t integral from R1 to R2 dr over R. All right. Well, the integral of dH, that's the simplest one we can do. It's just H, and we evaluated H1 and H2. We're going to get H2 minus H1. Integral of 1 over R dr is the natural log of R. So this will be 2 pi t natural log of R2 over R1. Here I've just evaluated it at these two bounds. And now I can rearrange because what I'm after is the transmissivity. So the transmissivity is equal to the pump rate Q 2 pi H2 minus H1 times the natural log of R2 over R1. And this is called time solution. And this is for steady state flow. To a well. And it says if I know the radius and the head at 2 points in my cone around my well, and I know the pump rate, I can calculate the transmissivity. So I need head at 2 wells. Within my drawdown cone. And my pump rate. And I can get the transmissivity of my aquifer from this equation. So this is the simplest case. If I've been pumping forever, my drawdown cone has not changed, and I happen to have 2 observation wells in my drawdown cone, then I can calculate the transmissivity.
So if you're going to delineate R1 and R2 based off your 2 wells, is there a rule you have to follow to designate which one is, or is you just choose?
Let me move back up here. I'm not sure I follow. So what's the question?
Say you have R1 is close to well and R2 is close to well. Is that just arbitrary that you chose, or?
Yeah, it doesn't matter as long as H2 corresponds to R2 and H1 corresponds to R1, it doesn't matter which one's closer or farther away, the signs will all fall out. Yeah. It turns out it won't matter. But all right, so this is a really rare situation. We hardly ever get to use the time equation, but it illustrates, oh, in that case, we can just consider this radial flow and we can just use Darcy's law. All right, let's take a quick break and then we will look at the transient case and we will look at what I'll call the basis for almost all pump tests that we will use. All right, and this is called the Tice equation. Time and Tice, man, it's really close. All right, 5-minute break. Okay, so we're back and now we're gonna talk about transient flow. So first of all, let's recall our assumptions. All right, I want to drill these in here. Homogeneous, isotropic, fully penetrating well, fully screened, well across aquifer. It's not, I wouldn't call it terribly common. So there are tricks we play when we're not fully screened. But these are the assumptions we have to make to solve the equation for this setting. And another one is a constant pump rate. Now, in the field, we're relatively constant, but it's hard to keep your pump rate constant. So here's another place where the real world and this mathematical world don't quite match up. All right, these are major assumptions. Now for the Tice equation, there's another caveat here. Couple ones. So here, this is transient flow. So we're saying that things are changing with time. But the big thing here is that we're saying it's happening fast. So all the water we pump out is coming from storage. There's no recharge from up above. There's no, the only place that water's coming out of is from storage from the aquifer. So all water from storage. And this implies no effect of recharge. This turns out is not a horrible assumption. If things are happening fast, it's fine. All right. And things are. We pump over the course of a few hours. We're not getting a lot of recharge over those few hours. Almost all the water's coming out of storage then. All right. So recall that our governing equation here was S over T dH dt is equal to D squared H dr squared plus 1 over R dH dr. All right, so this is ingredient 1. Ingredient 2 are boundary conditions. So what we say is that our head is equal to H naught at R equals to infinity. All this means is that there's some distance out there which our pumping is not affecting. All right, and at that distance, our head is equal to the initial head level. Again, this is fine for sort of short time pumping intervals. And initial conditions are another thing we need to have. That is that H is equal to H naught at R, all R for T equals to 0. So this is how we write these boundary conditions. The head is equal to H naught at some, for this is some point in space that we've defined, R equals to infinity, and for all T. Here, H is equal to H naught at, for all R at T equals to 0. And whenever you see a T equals to 0, you know that's an initial condition. That's our starting point. So we got a governing equation, we've got an boundary condition, and we got initial condition. All right, so the solution to this governing equation, subject to these initial and boundary conditions, it gets named after the white dude who developed it, Tice equation. And most importantly, it's a solution to this governing equation. All right, and okay, so this is an analytical solution to this groundwater flow equation subject to these boundary conditions. We call it the Tice equation, all right, or the Tice solution. This is a U, and we'll talk more about this integral here in just a sec. It goes from U to infinity. All right. Let's define a few things. Here, U is equal to R squared S over 4 times T times little t. So this is an infinite integral, all right? It starts off at this value U and gets evaluated all the way to infinity. All right, this is a famous integral, and it has well-known solutions. So this, if we focus in here on this guy, so this integral of U to infinity e to the minus x over x dx can be approximated with an infinite series. All right, a power series. If you recall back to calculus 2, this is a power series. And I remember being in calculus 2 and being like, God, these power series, what the hell are we learning them for? Well, if you want to solve these kind of equations, you can do it with these power series. All right, and this keeps going on and on and on. All right, good news for you. Some poor math person has already solved this power series, and this integral is a well-known thing, and we call it, actually, we're going to call it W sub U, which is the well function. Now, back in the day, when Jim Sears started working, not even sure if the Tice equation existed yet. It did. I'm joking. Barely. It was hot off the press. All right. And this well function was really hard to calculate. So probably some poor graduate student in the math department had calculated this infinite series out to 5 decimal points for a whole bunch of different values of U. And so what you would do is you would calculate your U, and then you would go to this table of well function for the well function, and you would find out what the value of this infinite series is for your value of U. All right, today computers will do this infinite series for you. All right. We'll probably still use some tabulated values, or we'll probably use a plot of the well function that I've made. All right, so the bottom line is the way we generally see these drawdowns is this way. So here's S, which is the drawdown, is equal to Q over 4 pi T times WU, all right? Where U we've defined up here. So U R squared S, big S here, over 4T and little t. All right, Q is my pump rate. T is transmissivity. What else do we got to define here? And S is storativity. Here for a confined aquifer, it's SS times B. All right, so let's think about what this does. This allows me to calculate the drawdown from a well pumping at some rate Q, all right, at any radial distance at any time, as long as I know the transmissivity and the storativity of my aquifer. That's what an analytical solution allows me to do. I can predict. I want to gain predictive power. Well, if I know T and S, I can predict the drawdown at any point in my aquifer from this pump rate.
Is that N equals or U equals?
U. Finch says, right, your U's better. Fair enough. That's a U. Okay. So let's do it. Let's do it. So let's do an example. You've got a well, let's do this. This is well A. All right, and it's pumping at, here's an observation well. This distance here is 134 meters. And Q sub A equal to 400 meters squared per day. And it's been doing this for 48 hours. The transmissivity of this aquifer is 1,000 meters squared per day. And the storativity is 8 times 10 to the minus 5. All right, so calculate S, the drawdown at the observation well from pumping at point A after 48 hours. And to do that, you're going to need some values of WU. Somewhere I have a bunch of them, but where is that? So here is what we call a type curve. So what you do is you would say, okay, I calculate U to be something. Then I can calculate what 1 over U is. And let's say 1 over U is equal to 10. I'd come up here and I'd say, okay, my WU is equal to, here's 1, this would be 2. So this is how we pick off what our WU is. So did anybody get a value for U yet? For U. So what's 1 over U? $8,748. Let's look at it here. We should make it, so this would be meters squared. This is unitless. For transmissivity is meters squared per day is this unit, and then T is the days. That's good conversion in your head. You must be Canadian. Okay, so 1 over U, 5,569. So this is 1,000, 2,000, 3,000, 4,000, 5,000. We'll go up here. Oh, that's close enough to 10. So I'll just write that down. WU Well, that's a good question. So what are the units of U? I have R squared, so that was 134 meters squared. What's U? Times S, which is unitless, over 4 transmissivity. So we had 1,000 meters squared per day times the number of days, so 2 days. So those cancel and U is unitless. So WU is unitless. Okay, so what'd you get for a drawdown? Were you gonna say something, Finch?
Yeah, I got it to be 0.0318.
You got 0.0318.
I just included more sig figs.
But did you guys say 0.32 or 0.032? So Finch, are you 0.318 or 0.0318? Because those are two different numbers.
I got 0.0318. Let me double check. Yeah, I got 0.0318. Because
So
it's 400 divided by 4,000 pi. Or
right,
roughly 1 over 10 pi, which is 0.0318.
I think it is, so the 4's cancel and it's 100 over 1,000 or over 3,000. I think it's I don't think there's a 0.0. I think it's 0.318. This is 10 to the 2. This is 10 to the minus 3. That'll be -1, not -2. So 0.32 meters. All right, great. This is meters cubed per day. This is not U. So Autumn says, why is my drawdown, right? The drawdown is 400 meters cubed per day divided by 1,000 meters squared. The days cancel. I end up with meters up top, and WU is unitless. So I end up with meters. U sub A is unitless, but S sub A, the drawdown, is in meters. All right. I've got another well B pumping at 200 meters cubed per day for 48 hours. What is the drawdown? What is the drawdown for a well at B? It was 200 meters cubed per day. All other values, the aquifer values are the same. And I'll just highlight that U, and this one is at 100. Actually, let's just keep it the same. It's at the same distance. Well, maybe. I don't see any reason why it's not. So what is it? 0.15.
Where did you get that 10 from? That's on the end.
That's the value of the well function, WU.
Where did you get that?
So Finch is asking where I got WU, and this is extremely important, so I'm gonna go over it again. All right, so we calculate U, right? And so that was whatever this number turns out to be. So what did you guys get for U?
I got 1.34 times 10 to the -6.
So I am hearing two different answers. So 1.8 times 10 to the -3. Let's see, my storativity is 8 times 10 to the -5. All right. And then, so this is my value for U, 1.8 times 10 to the -5. And then U, or 1 over U, is what? That is a 3, can't you tell? Oh. So what's 1 over this? I think it was 5,000 something, right? 5,559. All right, so Finch, I calculate U. I calculated, and then I just divided it. I divided 1 by U here. And then I came over here. Here's my graph of 1 over U versus the well function. So here's 1,000, 2,000, 3,000, 4,000, 5,000. So I go straight up from 5,000. It's about here. Come across close enough to 10. All right, so my WU, my well function, for that value of U would be 10. Does that make sense?
Yeah.
All right, so SAB 0.159. So now, what is the total drawdown at this observation well? So if I knew that I had 2 wells pumping, what would the total drawdown at this observation well be? So now I've got a much more complicated problem, right? I've got 2 pumping wells going at once. How can I calculate the total drawdown at this observation well? Is that okay? Because I developed this solution for only 1 well. The Tice equation considers only 1 well. So this is a really, really important, I can't actually like over dramatize how important this next thing I'm going to say is. Right? This is called the principle of superposition. And what it says is that if I have a solution to one differential equation, all right, I can add the solution from another differential equation to that. All right. So I can take the two solutions from Tice and I can add them together to calculate the total drawdown. So Autumn was right due to the principle of superposition. And this is a absolutely fundamentally super important thing for any kind of physical science, but for groundwater, we're going to use it all the time. And in high powered math speak, what the principle of superposition says, this is one word, it's not two words. The solutions to linear differential equations can be added together to represent more complicated settings. So for the Tice equation, we could actually have as many pumping wells as we want. They could be pumping for different amounts of time. They could be pumping at different rates. They can be at all different radius. We just calculate the drawdown for each one individually, and then we add them together. That's the principle of superposition. It makes our lives really, really much easier in groundwater. All right, so the total drawdown then, the total drawdown S sub T from both wells is just equal to S sub A plus S sub B by the principle of superposition. All right, so on Thursday we're gonna do the opposite. So what we'll end up doing, what we end up doing in a pump test. So the Tice solution allows us to predict the drawdown, given transmissivity and storativity, right? What we'll do Thursday is the inverse of this problem. We'll say, hey, we observed drawdown. We're going to pick the best transmissivity and storativity that make our model for drawdown fit our observed data the best. All right. That's the process of inversion. We're going to fit it by varying T and S. And we're going to do it with this graphical method. It's called curve matching. All right. It's really pretty simple and straightforward. What I want to do before we take off today is talk about various ways that our assumptions of a confined aquifer, all water from storage, fully penetrating well, all these things hardly ever are really true in the real world. All right. And so we're going to look at how the response can change. So the first one we're going to look at is a leaky confined aquifer. And what I want to do today and in this class is we're not going to get in. There are particular solutions for kind of a whole bunch of these different scenarios, say a non-fully penetrating well, a confined aquifer, or here my confining unit is leaky, it allows water to move through it. There's a million solutions out there to these pump test equations, and I don't have time to go through them all with you. We don't have time to learn them all. As you go on in hydrogeology, you may do a lot of these pump tests, and you may be in a setting where the Tice, we always start with the Tice equation because it's the simplest and it's the basis. And then we look and see how our response differs from that. And we decide, well, what am I seeing here? And what other kind of process might I need to include? So this first one says, well, what if not all my storage, so here's my drawdown cone, all right? Oh, that one was just terrible. What if not all my storage is coming, or what if not all my water is coming from storage, but I have some amount of water that's leaking out of my confining unit? What this says is my confining unit isn't perfectly impermeable, and I'm getting some volume of water adding to my aquifer here from the confining unit. And here's the kind of response that we'll see, and this will make a little more sense after Thursday. But if I plot drawdown versus time for a Tice aquifer, the drawdown versus time looks exactly like this type curve. So this is the shape of the drawdown versus time. It starts off and drawdown is really, really rapid. And then as time goes on, it planes off. All right, but it continues to increase. So this is what we call the Tice response. It is very rapid, tails off, but continues to increase with time. So this is what we call Tice response. This is our perfect confined aquifer response. What we see in this case where we've got leaking storage here is that we will start off along this Tice response because there isn't much chance for water to exit this storage. This is early time. Water that's going to leave this doesn't have time to leave. The drawdown cone is small. But as the drawdown cone gets bigger and bigger, and there's more and more time for that water to seep out of the confining bed, what do you think will happen? Will I see more or less drawdown in my well if I'm releasing water from storage from this confining unit, this leaky confining unit? So why? I mean, I don't disagree. I just want to understand the reasoning here. Remember, drawdown is how much the water level drops in the well. So we're going to, in fact, I agree, we will see less drawdown. All right, and why is that? Yeah, you're adding water from another place besides your aquifer, right? So there'll be less drawdown. So what we'll see in this setting is that the drawdown will start to tail off, and then it'll plane out, and sometimes it'll even reach just a fully flat, where all the storage, all the water that's coming into our well is being supplied by leakage out of this leaky aquifer. And this initial response, almost all aquifers show this early time Tice response. And the bottom line is this is because the sort of the fastest way an aquifer can give you water is by its own storage and by the decompression of the water and the compression of the porous media. That's the fastest way it can. So there's almost always an early time confined aquifer like response, just because that's the fastest way it can get you water. This other water here has to physically drain out of this aquitard down into the aquifer. So it takes a long time for it to get there. And it only manifests itself later in time. So this is the sort of late time. We'd call this the steady leakage. And this transition period here, we might actually be releasing water from storage. And the aquitard. So in general, when I've looked in our past pump tests at Lolo, we often see when we try and throw the type curve on it, we're going to see this kind of response where it's like we get a very early time Tice response and then the drawdown really planes off. And it's because whatever is on top there is not really acting as a pure confining unit. We'll also look at Thursday, we'll look at the expected response from an unconfined aquifer, all right, which basically looks like this for a while and then has another response. All right. I will sign off now since we're over time, and we'll see you guys Thursday. Bring we did our curve matching digitally last year because we were all online, and I actually think it worked a little better. So I'll bring the paper copy, but if you have your laptops on Thursday, things might go smoother. All right.